Alright, welcome back. In this video, we're going to go over the overview of energy coupling and glycolysis energy. Before we actually start glycolysis, which is the first stage in the metabolic pathway, we need to go over one more key component. It might be two, actually. I didn't look at my schedule, but I think it's just one. Most of the reactions in our body are not favorable. In biochemistry, it's all about reactions. Most of them are unfavorable and some are favorable. So let's go over what this means. Here's an example. You're not expected to know this yet, but what you should know is what delta G is and what it means. So in this example, this is a mechanism. This is a reaction here. Glucose plus phosphate turns into glucose 6-phosphate in water. You don't need to know this, but what is important is the delta G value here. The delta G value for this reaction is plus 13.8 kilojoules per mole. The number itself is not actually important, but what's important is the sign in front of the number. That's a bad arrow. The sign. It's positive. A positive delta G value means that this reaction costs energy to run. So it is unfavorable. Let me give you an example, like real life. I know this is a terrible picture, but it's a guy riding a bike, going uphill. You probably have noticed if you've ever ridden a bike, that when going uphill, it takes a lot of energy to do so. Or you're on the treadmill and you jam that incline button and you max it out. It takes a lot of energy. Your legs are going to hurt. It takes a lot of energy to actually climb or walk up that incline. It's the same concept. It's costing energy to do so. So you may be thinking to yourself, wait a second, our body is trying to make energy. The whole purpose of the metabolic pathway we're learning is to make energy, to make ATP. That's the end goal, and water. But that is the end goal, to make energy. Why do we need to actually spend energy to actually make energy? Well, it's the same concept as you need to spend money to make money. It's the same concept. To actually get ATP and actually get energy and produce energy, you have to put some energy in. Now, how does your body actually combat this issue? Because this reaction by itself will not want to go forward. It costs too much energy. Your body is very resourceful. It's not going to run anything unnecessarily, especially if it costs energy to do so. That is where energy coupling comes in. Okay, so some reactions in your body are actually favorable and release energy. Here's an example. You don't need to know this, but ATP plus water gets broken down into ADP plus P. So it's a hydrolysis reaction. The delta G value is negative 30.5 kilojoules per mole. It's the negative sign that we care about. A negative delta G value means energy is being released. It doesn't actually cost any energy to run this reaction. It is favorable. It'll just do it by itself. Your body's like, yes, I do want to run this reaction because it's going to give our body energy. It's like equivalent of going downhill on a bike. You go really fast. It's really fun. That's exactly what your body's trying to do. It likes that kind of reactions. It likes to go downhill. And that's what's happening. So, our body is basically saying, well, this released free energy will help me power the other unfavorable reactions in our body. Let's couple the reactions together so that one reaction can donate all of its free energy and power to the other, which is this. This is free energy. That's what delta G means. It's free energy. So in other words, it's going to use this energy that we have just created We don't actually create energy, but whatnot. This release of energy is going to go help and power this reaction, because this one's not going to run by itself. It needs some help. So that's what energy coupling is. This looks a little confusing. You don't need to know any of this. But what you do actually need to know is that the whole energy coupling concept. What we're doing is we're taking the first reaction from the first slide. It's the same thing with that positive 13.8 kilojoules. We're going to combine it with the other reaction, which is here, with a delta G of negative 30.5 kilojoules. And we're actually going to get our product, which is the glucose 6-phosphate, which we were trying to create in the first place right here. So we're going to use the energy released from here to power this one, this reaction here. So that's what we do. We are basically the reactant is glucose plus ATP, and we're going to get our glucose 6-phosphate, which is our desired product. And all you do is you just subtract the two numbers and you get the delta G value. Now notice that this delta G value is negative. So this reaction is actually going to release even more energy. Well, when it releases energy, this reaction now, this new reaction, when we just coupled it, since it's a negative delta G value, it's going to go power another reaction in our body, wherever it is. It's going to go couple with another unfavorable reaction. And this just cycles. And that's how our body runs. It is such an important concept in biochemistry. Without energy coupling, we would die. Because most of the reactions are unfavorable and they require energy to run. So this is a method for our body to actually conserve energy and to move reactions forward to get our desired products. Your entire body works like this. That's why it's important. Now let's switch gears a little bit. Let's talk about the glycolysis energy pathway overview here. Glycolysis, which we're about to go over in a few videos, is made up of 10 steps. The overall goal for glycolysis is to turn glucose, which we're going to start with, into something called pyruvate. That's the end goal, to pyruvate, from glucose to pyruvate. To do this, it takes 10 steps. And we're going to go over all 10 steps when we actually get into it. But here's what I want you to take away from this part right here. Steps 1, 3, and 10 have a large negative delta G value. It means it is very favorable. In addition, these are called irreversible reactions or rate-limiting reactions. Because it's such a large delta G value, these are steps 1, 3, and 10. When they're done, they're going to produce so much energy, it's going to power the rest of the pathway by energy coupling. So let's look at, for example, step 2. It's a little decrease here, so it is favorable, but very, very marginal, almost nothing. Well, to make sure this reaction happens, this step 1 is going to help power step 2. It's going to couple together. Because step 1 is releasing so much energy, let's put that energy to good use. And some of this energy is going to go to other pathways as well, which we don't really care about. But what I want you to take away from this is that steps 1, steps 3, and 10 are rate-limiting steps. Once we make the product, we cannot go back. Most of glycolysis is reversible reactions. For example, at step, say, 8, for example. Once we make the product in step 8, we can actually go backwards and go back and create the reactants if we need to. So you can go back and forth. But for steps 1, 3, and 10, once we create the product, there's no going back. We can only go forward. So they are called rate-limiting steps, and the reason is because the delta G is a very large negative value. So that's what I want you to take away with it. So in biochemistry, energy coupling is the king. That's how the whole biochemistry, entire course of biochemistry revolves around energy coupling. It's that big of a deal. And that's how it relates to glycolysis. So if you found this video helpful, please like and subscribe. Until next time, later.